How are we doing today? Hopefully everybody is doing well. So today we're going to be covering Radioactive Decay series. Now to get started on this, you do need to make sure you've got your notes, you need to make sure you've got something to write with, and then you're also going to need a periodic table. And then you may need a calculator, but your phone would work just fine for the math that we're doing today. Okay, so the Decay series, what is it? Well, the Radioactive Decay series is basically taking what you learned last class with Radioactive Decay and doing it in series. So you're doing it multiple times in a row. All right, so let's take a look at this. So it says, example 1 says a radioactive decay series begins with uranium-235, and it undergoes the following sequence of reactions. And so what they tell us is that we go with a beta, then an alpha, then a beta, then another alpha. So we're going to go through 5 different decays, which is why we call it a decay series. So I know that I have uranium-235. And I know that uranium is number 92 by looking at my periodic table. And it is going to undergo beta decay, 0, -1, E. Okay, you're like, okay, well, Mr. Oglesby, this is the same thing as we did last class. Well, yes, it is. We're just now going to do it multiple times in a row. All right, so 0, -1, E plus what? I've got a mass of 235 on the left. I've got a mass of 0 on the right, so I need to add 235 on the right. I've got 92 protons on the left. I've got -1 proton on the right, so I'm going to need to add 93 more protons here. So then I look at my periodic table, I find number 93, and I will see that it is NP. Okay, now I keep on moving along. But instead of just starting over with uranium, I'm going to start with the last thing that I ended with, that substance that was produced from the previous decay. So I have 23593 NP, and it's going to undergo another beta decay, 0, -1, E. Now what do I produce? Again, we check our masses. We'll find that we have 235. We check our atomic numbers, and we'll find that it should be 94 that we're needing right here. So I find that on my periodic table, Pu. All right, keep on going. So now I've got 23594 Pu, and it is going to undergo alpha decay, because that was the next one in the series. So an alpha particle is 42He. Now we're going to take that, and we are going to figure out what we need to add. Well, we need to add 231 to our mass, and we need to add 92 protons. Okay, well now we're at uranium-231. So if you compare that to what we started with, what has happened? Well, we've lost 4 mass. Okay, so this is what happens with our decay series. Is we're going to start to see the elements, and the elements that are produced are going to start to change. Okay, so now I'm in step 4 here, so I'll start with uranium-231. And it's going to undergo another beta decay, 0, -1, E. And so we're going to need a mass of 231, and we're going to need 93 protons. Okay, so we're back to that, but again, we've lost 4 mass in the process. Now I start with that last one there, so 23193 in P, and it is going to produce, under alpha decay, 42He plus what? Well, we look and we got 227 for our total mass, and 91 for our total atomic number, and we get Pa. And so that would be our final equation. So then what is the final element? Our final element is this right here. So that's what we do for a decay series. We're basically just taking those decays that we have, alpha, beta, gamma, and we're going to go through them multiple times until we end up with the final one that we were looking for. Okay. All right, so now what we're going to do is we're actually going to talk about half-life. So now that y'all know how to do decay series, let's talk about half-life. Well, half-life is actually what we use to do a carbon dating of different substances. So we're trying to figure out how old a substance is. And what we do is we use half-life. And half-life is basically just how long it takes for half of that substance to go through some kind of decay. All right. So when I'm looking at the half-life of a substance, basically I'm looking and seeing how those isotopes went through a decay series. And what I know is that what we've learned is that certain substances undergo decays in the same way. So they'll start to go, for instance, the uranium 235 there, it will undergo beta, beta, alpha pretty consistently. And so they can use that to figure out predict what the life of the substance would be, because over time, we're going to end up with different substances. And that's how a half-life actually works. That's how we can actually use that to figure out the age of something. So the half-life of an isotope is the amount of time that passes before half of that isotope is going to decay. So it's exactly what it sounds like. It's basically half of the substance, how much time it takes for it to do that. Now, all atoms, all radioactive isotopes are going to slowly degrade over time. Some things are actually very, very quick. For instance, francium just takes like 12 seconds to go through a half-life. Okay? Whereas if I take something like carbon, it's thousands of years. Okay? So depending on the element and depending on how stable it is, the slower it goes or the faster it goes. Okay. Now, a most common example of isotopic dating is when an archaeologist will date an artifact. They're trying to figure out how old the artifact is, what time period in history did it come from. And so they'll basically analyze some of the substance that's there, and they'll see how much of the different elements that we find, and then from there they can figure out what the age of that substance is. Okay? So with radioactive dating, what we find is that the process, this is the process we use to get an approximate age of the object. And it's actually fairly close to being pretty accurate with how close we are. So again, here's the example of carbon-14. Carbon-14 has a half-life, which means half of that will be gone after about 5,730 years. So one half-life is going to be 5,730. So what does that mean? Well, if I started with 10 grams of carbon-14, after 5,730 years, I would have 5 grams of carbon-14. The rest of it will be a new substance, a new element. If I take that and I go through another half-life, so I wait for another 5,730 years, I'll be left with 2.5 grams. Wait for another 5,730 years, we'll get 1.25 grams. So I can look at this and I can actually figure out how old that carbon is based off of how much is left over. Okay, so that is your lesson on radioactive decay series and half-life. Let us know if you got any questions, and I hope y'all have a great rest of the day. Bye, y'all.